Herkese merhabalar. Dönem arasından sonra Nano Open'a bugün tekrar başlıyoruz. Bugün çok özel bir konuğumuz var. Teşekkür ediyoruz. Yoğun programın arasında bizi kırmadı, zaman ayırdı. İzmir Yüksek Teknoloji Enstitüsü Mühendislik Fakültesi Dekanı Profesör Doktor Mustafa Demir. Hocam hoş geldiniz.
Hoş bulduk.
Ee,
Herkese merhabalar, günaydın.
Biz bugün Nano Open'ın başlangıcını 9 Ekim'e getirmeyi de özellikle istedik. Bir süredir düzenlenen bir etkinlik olan Nanoteknoloji Günü, nanoteknolojinin günlük yaşamlarımıza kattığı zenginliklerin tanınması ve kutlanması amacıyla düzenleniyor. Bu etkinlik 10 üzeri eksi 9 metrelik nanometre ölçeğinden ilhamla her yıl aynı günde, yani bugün 9 Ekim'de kutlanıyor. O yüzden biz de bunu fırsata çevirmek istedik ve Nano Open'ı da bugüne denk getirdik. Hocam tekrar teşekkür ediyorum. Mikrofonu ve ekranı Mustafa Hoca'ya vermeden önce hakkında kısa bilgi aktarmak istiyorum. Mustafa Demir lisans eğitimini 1999 yılında Boğaziçi Üniversitesi Kimya bölümünde, yüksek lisans ve doktora eğitimlerini ise 2001 ve 2004 yıllarında Sabancı Üniversitesi Malzeme Bilimi ve Mühendisliği programında tamamlamıştır. Demir, doktora sonrası çalışmalarını Almanya'nın Mainz kentindeki Max Planck Polymer Araştırma Enstitüsü'nde yürütmüştür. 2007 yılından bu yana İzmir Yüksek Teknoloji Enstitüsü'nde görev yapan Demir, disiplinler arası eğitim ve araştırmaların yürütüldüğü enstitünün mühendislik fakültesinde dekanlık görevini sürdürmektedir. Profesör Doktor Demir'in hakemli dergilerde 110'dan fazla yayını bulunmaktadır. Başlıca araştırma alanları nano yapılı malzemeler, polimer bazlı nano malzemeler ve jeotermal enerji uygulamalarında polimerlerdir. 2013 yılında Türkiye Bilimler Akademisi tarafından verilen Genç Araştırmacı Ödülüne layık görülen Profesör Doktor Demir, Elsevier ve Stanford Üniversitesi tarafından yayınlanan dünyanın en iyi %2'lik araştırmacı listesinde yer almaktadır. Hocam tekrar hoş geldiniz. Ekran paylaşımını durduruyorum ve size devrediyorum.
Çok teşekkürler Nokta Hanım, güzel sözleriniz için. Ben de herkese tekrar günaydınlar diliyorum. Sevgi ve saygılarımı ileterek ekranı paylaşıyorum. Sunumum İngilizce olacak. Ondan sonra belki Nokta Hanım şey yapacak, idare edecek ama belki son soru cevap kısmında Türkçe'ye geçebiliriz. Ekran geldi mi hocam?
Geldi hocam ve ilerledi.
Peki. Okay, good morning again, everyone. Again, my name is Mustafa Demir. I'm working at İzmir Institute of Technology and Material Science Engineering Department. Today I will have a talk. And first of all, thank you for your participation. It is really my pleasure to be among you to share our recent results in front of such privileged audience. I checked the list of the audience. So the title of my talk will be Colorimetric Mechanical Sensors based on Polymer Nanoparticle Systems for various applications. So in the cover slide, you see one panoramic view of our campus area, where our campus area is located in Urla Peninsula of İzmir. So we are very close to beach area. So it is a very nice place, and it's a piece of paradise in the world, I think. So today is 9th of October, as Nokta Hanım said. So today is Nano Day. Nano as a prefix stand for 1 out of 1 million. Okay. So and the 10th month of the year and 9th day of the month. So it's 10 to 9. This is Nano Day, and I celebrate your Nano Day. I wish you a good day. Okay. I hope it will be my talk will be successful and will be beneficial for you. So in this slide, you see mechanical failure of material systems. On top and very left-hand side, you see building affected by earthquake. Earthquake is an important issue for our country. It was important, it is important, and it will be important, unfortunately, for the coming future, I guess. So next, you see a petroleum platform. So you see a mechanical failure of such big system. And next, you see a mechanical failure of a bridge and mechanical failure of a part of aircraft. and mechanical failure of an item in a big machinery system. So it is important to know the location and extent of failure. By the way, such kind of mechanical failure does not always occur catastrophically. It doesn't occur all of a sudden. So first of all, it hints information before. There are some stress points on the material systems. The failure occurs first, the stress points, rather than failure of the entire system. So imagine that these stress points are known, and then they are coated with some material, and material gives some color upon mechanical force and mechanical change. So it hints about the failure of the stress points by colorimetric change. It will be very easy for us to know the health of this of any structure. In fact, there are many different mechanical sensing mechanisms. They are already commercially available in the market and in the literature. So piezoresistive materials, piezoelectric materials. So for example, resistivity changes upon application of a mechanical force, mechanical impact, okay? Or electricity changes upon application of certain amount of pressure, or capacitive inductance change. They are already known. And for such kind of acting mechanisms, we need some machinery and electrical circuit. Okay, we need to have such kind of complex electronic circuits and a system for sensing and for actuation processes. So imagine that you have a colorimetric sensor and you understand such kind of mechanical failure or such kind of application of any type of mechanical force on top of material by simply changing the color. Okay, color change hint about the structure of a material system. In fact, this is something common in nature. Okay, in nature there are very good examples. Chameleon, for example, is a good example for such kind of physical phenomenon. So chameleons, it perceives the color of its substrate staying on it. Then it changes its color according to the color of substrate, such that it becomes somehow invisible to enemies in nature. Huh? It's a kind of protection mechanism for themselves. So physical coloration occurs here in the system. There is no any single molecule of pigment in the material. So how comes and how does chameleon change the color of skin? So the basic explanation is as follows. The skin is an elastic material. So there are some protein crystals named guanine on top of it. There's a kind of protrusion on the surface, and the distance between the guanine crystals can be adjusted by skin. Okay, if the size of the length of two guanine crystals is comparable with the wavelength of visible light, it is possible to change. It is possible to control the colorimetric change. Okay, it is called physical coloration, and I'm gonna show you several examples. So this is the outline of my talk. In this talk, I'm gonna present you three different, say, pigment system. The first one is triboluminescent materials. Okay, under this title, I'm gonna present you two different chemistries: europium tetrakis-triethylammonium and copper isothionocyanate bipyridine triphenylphosphine. The names are long, and I'm going to say that red triboluminescent material and blue triboluminescent material during the talk. In the second part, I'm going to mention you about structural coloration as the chameleon does. Okay, so in this talk, I'm going to show you synthesis of silicon dioxide colloids particles and integration of these particles with polymers such that it is possible to obtain some iridescent or non-iridescent type of coloration. In the last part of my talk, I'm going to present you surface plasmon, particularly gold chemistry. Gold, metallic gold, bulk gold has yellow color, as you know. So when we reduce size into nanometer size, say 10 nanometers diameter of particles, it has red color. Once the particles come together, form larger aggregates, the color turns into blue, and it's a perfect material to synthesize pressure sensor in polymeric systems. Let me begin with the first part of the talk, triboluminescence. From the epistemological point of view, this word can be divided into two parts, tribo and luminescence. Tribo in ancient Greek is it stands for to rub something. Okay, if you rub something, so to silicon, to quartz crystal, for example, you see a flash of light. Okay, this is the oldest way of making fire. Okay, then the luminescence, it comes from Latin word and it means light. Okay, so when light emission occurs by heating, it is called incandescence. So a good example is charcoal. When you're grilling, so you see the color of charcoal turns into orange, red, and blue, okay? We see black body radiation of charcoal, okay? So if you have luminescence without heating, it's called emission without heating, it is called luminescence. If luminescence occurs by mechanical force, it is called triboluminescence. So there are many good examples in nature showing triboluminescent behavior. Triboluminescence means you give an impact to mechanical force and you see a flash of light, like lightning, okay, in nature. This phenomenon has been known more than several hundred years, but there is no established theory yet, as far as I know. But I know one textbook explanation. It is as follows. So you have a crystal, and mechanical force is applied to the crystal, and crystal is broken, say, into two parts. And you obtain two oppositely charged Neve surfaces. Since they are oppositely charged, there's an electrical potential in between. And this potential excites atmospheric nitrogen, and we see lightning, and we see emission of excited atmospheric nitrogen. Okay? So in order to have lightning, we need to break some bonds in the crystal. Okay, then we have a charge separation, and these are the must for the occurrence of this mechanism. As I said, there are many good examples. So very nice kid demonstration. In the dark room, please have a sugar cube and hammer on it. And in dark room, you see a blue flash of light. Okay, even simple sugar cube. Okay. So both organics and inorganic crystals show such behavior, like coumarin, recyclonol, or any other type of metal oxide show this behavior. So the highest emission is obtained by European tetrahydroethyl ammonium. Okay, so the idea of this ratio, this has been known as a smash glow materials in the market. The idea in this research is to transfer this function into polymeric systems. Okay, into complex polymeric flexible systems that can be processable at moderate temperature. So again, two crystals, one red and one blue, and these crystalline materials somehow associated with transparent polymers like polymethyl methacrylate, polystyrene, polyurethane, and for different end-use films, fibers, and beads in our research. I'm going to share you a movie. Then this movie you can readily understand what I'm talking about. So these are the red and blue crystals. So they are highly fluorescent under UV light. And when a mechanical force is applied to the crystals, you see a flash of light, okay? So my student Anil Ingel is applying mechanical force on these crystals. So you see, so when he applies force, you see emission of light. And these are crystalline powder, okay? So for red one, since we don't have enough time, for red one we have similar phenomenon, but the emission occurs in blue, okay? So there's a flash of light. The lifetime of this emission is very short, okay? So we have to establish a system to measure spectrum, okay? So we have a cross-section of this setup, you see on the left-hand side. We have a black box, okay, made by polymethyl methacrylate. And on the black box, we have a tower, 10 centimeters of cylinders, okay, transparent cylinder. So we can make a tower. On top of the tower, we have a steel ball. We know its weight. So we release the ball from this height, okay? So it undergoes a free fall. So we know the potential energy turns into kinetic energy. So free fall stuff in basic physics. Then it hits to the sample holder at the bottom. So we have a flash of light. Since this occurs in a dark box, okay, it is possible to measure spectrum via fiber optic spectrophotometer. So on the right-hand side, you see two representative triboluminescence spectra of of red and blue emitted organometallic crystals. For the synthesis has been known more than say 50 years. We begin with 1,3-diphenyl 1,3-decatone propan, then using europium nitrate and triethyl ammonium. We mix them, they undergo crystallization at low temperature. Then we have an organometallic compound. Europium is at the center. Central europium atom is surrounded by ligands. And pay attention, the distance between europium and nitrogen is quite long. The distance is around 2.5 angstrom. Remember that the carbon-carbon bond is 1.4 angstrom. It is quite long compared to carbon-carbon bond. So we see a representative electron microscope image of crystal on the left-hand side. And the crystal have a rectangular prism. The length is 400 nanometers and the width is 30 nanometers on average. So we have photoluminescence of this material in solution. It's quite nice signal. So in the middle, we see triboluminescence spectrum of the particle. So we have free fall of the ball from 20 centimeter to 40 till 200 nanometers. You see, as the intensity, as the height increases, the intensity of this emission increases. It shows that it's a very a promising material for being mechanosensor applications. Okay. So for blue emitted copper isothiocyanate bipyridine triphenyl phosphine, so we have similar story. The synthesis is known and we carry out synthesis with undergraduate students in our lab. So the key word is as follows for both systems for triboluminescence applications. In order to have emission, the crystals should be non-centrosymmetric. That means when a mechanical force is applied and you see a breakage of the crystal, so you need opposite charged Neve surfaces, okay? So it gives you this opportunity. So both crystals are monoclinic and having different unit cell dimensions. So the question is, these crystals are known and synthesized. How can we associate with polymers? One remedy could be as follows. You can dissolve crystal particles in a polymer solution, and you have a solution of polymers and pigment material. Then you cast on the surface, you obtain film. And this is called embedding or blending. Second could be surface impregnation. So you have a film, and film is immersed into a solution. Then the particles, crystalline pigment particles, adhered on the surface of the film, okay? So you see triboluminescence performance of these composite films, okay? So on the left column, you see the ones prepared by embedding with polymethyl methacrylate, polystyrene, and polyurethane. And the right column shows the more or less same material with different composition, polymethyl methacrylate, polystyrene, and polyurethane. Pay attention, please. In embedding one, you hit the sample, but you have no any emission. Easy to understand, the triboluminescence is associated. It originates from the crystal, not molecules. In solution, we have a molecular dispersion of triboluminescence compound, and we don't have triboluminescence performance. In surface impregnation, we do have triboluminescent signal, you see, in the first drop, and we apply second, third. So in the first 7 drop, we observe triboluminescence signal, okay? So the signal diminishes as the number of drops increases, and it is similar for polystyrene, polyurethane. In polyurethane, we need 17 drops for diminishing the entire triboluminescence signal for the system. For the blue one, we have similar story. So surface impregnation, as you see, yields higher triboluminescence response, and we have a sequence. Polyurethane is better than polystyrene, better than polymethyl methacrylate. You are going to see the reason in a minute. So in this slide, we see the size of crystals during application of mechanical force, initial and first, 7th, 11th, and 17th drop. You see the size distribution is getting smaller and smaller and smaller. So, and as it gets small, we don't have enough triboluminescent signal. So because particle size gets small, then you break it, you have lower number of breakage during mechanical force, and you obtain less triboluminescence signal. It is understandable. So in this fluorescent microscope image, you see both composites prepared by embedding and surface impregnation. In embedding case for the red one, for example, you have seen red emission from every pixel of the image. So the molecules are well dispersed over the polymer volume, but we don't have triboluminescent signal. For surface impregnation, you see, depending on the concentration, you have different islands. And these red islands, they refer the existence and the presence of triboluminescent crystals. Okay. So surface impregnation allows to hold crystal at the surface. Why polyurethane seems much better? Because it has hydrophilic and hydrophobic domains, and this difference, the reaction to the humidity, creates a porous surface on the structure. Okay. So for the conclusion of the first part of the talk, I showed you integration of triboluminescent material with polymers and via two ways, and surface impregnation is one of them and allows to generate high triboluminescence response. And polyurethane seems the best among the other two transparent polymers, and they can be used as an potentially impact sensor material. As you remember, increasing the height of the ball increases the intensity of the triboluminescence signal. For the second part of talk, in this part, I'm gonna present you structural coloration. So the motivation is again coming from nature. You know maybe Morphomenelaus butterfly, okay? So it has a very deep and attractive dark blue, okay? So if you are curious, when you look at the wing of this butterfly by microscopy, you see some periodic plates. So if you increase the magnification slowly, at the very end, you see uniaxially aligned protein fibers on the wing, okay? They are equidistant, and the distance is around 150 and 200 nanometers. So you remember from the basic physics course, Bragg's law. If you have an ordered material like crystalline material, you have a coherent scattering of this material. We call diffraction, okay? And this is called Bragg's law. And we have Snell's law when a light impinges on a solid surface and dense medium. So the light refracts to the normal, okay? So if you write the equations and if you solve and you end up with this equation you see on the slide, Bragg-Snell law. On the left-hand side of this equation, you have m. M is an integer, okay? And lambda is wavelength. We are in visible light. Wavelength means color, okay? And on the right-hand side, you see a complex root, and you have a d. D is the d spacing in periodicity, d spacing between interatomic distance, say, okay? So as you see, lambda, the color is proportional with distance of the periodicity. So we know the boundary conditions are I perceive in a very limited range of wavelength from 400 nanometers to 800 nanometers. So if we write boundary conditions on the wavelength on the left side of the equation, D should be 150 and 300. That means if you are able to fabricate a material on the surface, you have a periodicity with 150 and 300, then you're able to give color without having any pigment, okay? How can we do that? The literature is full of giving the synthesis of various types of colloids with different chemistries. So we use the synthesis of colloids. And if you arrange these colloids can be arranged via two ways. If there is enough time and enough energy, and if you are patient enough using the appropriate system, it is possible to pack them in a like a crystal, okay? You remember the metallic or inorganic crystals? The atoms are replaced by large colloids. So if they pack like the crystal, they are called photonic crystals. Langmuir-Blodgett method allows you to fabricate such crystals. If you have a quasi-ordered or disordered structure of these colloids, they are called photonic glass, okay? So photonic glass is a non-iridescent type, gives non-iridescent type of material. It gives angle independent type of coloration. For photonic glass, you have angle dependent, like you can consider the skin of fish. Skin of fish is an iridescent material. It is made up of photonic crystal. One piece of work from literature, on the very left-hand side, you see a picture. So there is one transparent elastic polymer, and one region is coated with colloidal crystal shown by orange. If you stretch, it turns into yellow. If you stretch more, you have seen blue shift, it turns into blue. If you release, then you have the recovery of the color, recovery of the material and recovery of the color, because the interparticle distance change, it turns into yellow, then it turns into originally orange color. So when you apply force, since this spacing changes, you are in the limit between 150 and 300, so it is possible to give color, and if the substrate is elastic, and it's supposed to return back, okay, to back to original color. In our case, we took opportunity for the synthesis of silica particles using Stoeber method. Stoeber method has been known more than several decades in literature. We begin with tetraethoxysilane, undergoes hydrolysis and condensation, then you obtain silica particle, okay? Silica colloids, and they are usually uniform size if you are careful enough about experimental conditions. So these colloid solution is in water, and it is sprayed on a surface, and we apply a mask of polydimethyl siloxane cast on the surface. Okay, the surface is entirely covered with polydimethyl siloxane. After curing step, we peeled off the material from the surface. On top, you have polymer. At the bottom, you have photonic crystal, but photonic crystal structure is frozen in the elastic polymer. So the electron microscopy images of the silica particles, the size lies between 160 to 300. We are in the safe range for coloration. So in FFT, we don't see bright spots. That means the particles are not well ordered. They may be quasi-ordered or disordered. So you see the spectrum of these, UV spectrum of these colloidal system. So by the way, they don't have any scratch resistance at the moment. You see yellow and blue color and gray color. You see various type of colors depending on the size of the silica particles, and they are non-iridescent. That means there is no change of color depending on angle. So in optical microscopy image, you see initially the image of the original composite material. You apply for elongation of 20%, 40, 60. You see extension of the colloidal systems in the uniaxial direction. Then after releasing, then after stretching, you return back more or less the same condition. So I don't know whether you can see on your screen, but in 40 and 60% extension, you see slightly green and slightly blue colorimetric change. In transmission spectra, you see original one, the black one. If you apply extension, same material, at 60% extension, you see there is already opaque material, okay? So I think I can show this phenomenon on the picture. So this is the sample prepared my PhD student, Gökhan Topçu. So he was a very clever guy. So before his PhD exam, he prepared a sample and he put the capital letters of my name on PDMS. You see, MMD is the capital letters of my name. So he was quite gentle for me, but believe me, he had really quite hard time during the exam since he is doing such kind of sampling. So if you measure transmission of this material, you see transparent material, and then you release back its opaque, apply, and you have on and on off type of change in transmission of the material. What's happening in this material when you apply force in PDMS? PDMS is quite soft. It released from the surface of silica particles. You see, please, on the right-hand side. So in between, there's a gap, and gap is full of air, and we see optical scattering of air because the refractive index or air is much less than silicon. Polydimethyl siloxane, this air causes optical scattering, and we see opaque material. If released back, it returns back to its original transparent condition. So this was a sampling prepared by spraying method. We have Langmuir-Blager system in our lab. In LB system, you have a substrate. You put the substrate in a colloidal solution. Then you release back quite slowly, such that colloidal particles are packed on the front and back side of your substrate. So we use glass slide for different various size of silica particles, 180, 220 and 290. So you see different colors, okay? So, and they are iridescent color, and we somehow sandwich this photonic crystal in between two glass slides. since they don't have any scratch resistance, we had to be quite gentle, and we put using shrinks, we put some monomer inside the sandwich, inside space of the sandwich. It was polyethylene glycol phenyl ethyl acrylate. So then we apply photopolymerization. Okay. Then at the end, after polymerization is finished, we obtain transparent and elastic material. So one representative set of image of our material. On top you see silica particles, and the D part shows the cross section. On top you see colloidal particles, and the order is somehow distorted. In the below you have polymeric stuff, and the colloids stay on the composite film on substrate. So one photographic image of neat polymer. You see this one image is divided into two by dashed line. Above dashed line you have a neat polymer, and below dashed line we have photonic crystals having blue color depending on the size of the particles, and it is in polymer, and the structure of the photonic crystal is frozen in transparent and elastic polymer matrix. Okay, so on the right hand side you see yellow of the version of this sampling. So they are iridescence. When you change angle, you obtain different spectrum. The color of the spectrum gives the original color of the material here. So one can follow the lambda max change. The lambda max means the peak point of this spectrum. So depending of the strain, you can readily see the lambda max varies from 580 to 500, and these colors you see on the colloids are original color. We have a variation between yellow and say green upon application of mechanical stress. For the conclusion of the second part of my talk, we obtain various colors via structural coloration, and using spraying and Langmuir blushes, we obtain the photonic glass and photonic crystals respectively. So they were readily successful transparent into transparent elastomeric polymers, and they can be used as a stress sensor, as you witnessed. So the last part of talk and the last chemistry I want to talk you today is gold nanoparticles. As I said at the very beginning, the gold itself has metallic bulk gold has yellow color. So when we reduce size into say 10 nanometers, so we have surface plasma resonance. We have seen collective oscillation of electrons, okay, in the structure. So upon electromagnetic application of electromagnetic wave, okay. Okay, this is surface plasmon. When the surface plasmon come together to form large crystals, aggregates, we see coupling of this plasmon, and the color changes from red to blue. And it is a very good promising material for having pressure sensor. So imagine that you have blue colored aggregated gold particles in a polymer matrix. Then you apply stress, you apply pressure, say, so, and you somehow succeed to individualize the particles. The particles are individual after this application of mechanical stress, then it turns them into red. So we are using polyacrylamide. It's transparent, it has bio-nature, and it is self-healing polymer. So gold clusters are mixed with polyacrylamide. You have a blue, say blue composite film, like litmus paper. Then you apply a certain amount of pressure, okay? So 40, 80, 120, and 160 PSI, okay? So for application of pressure, we are using very simple apparatus. You can find this apparatus in any vibration spectroscopy lab for sample preparation of FDR samples. It is possible to apply pressure on the composite system. As you see in the spectrum, we have seen all colors in the spectrum in the material upon application of mechanical stress. So electron microscope images before and after application of pressure. Before application, you see large aggregates. The particles are close to each other. We see coupling of plasmon. Then after application of pressure, you see the particles are separated from each other, and we see surface plasmon, and we see red color of the gold nanoparticles. So we have seen 6 different samples, originally prepared by Blue. Then we apply force, and the same set of experiments, you see reproducibility of the material. You apply force, then blue color turns into remarkable red, and one can writing an apps for smart mobile phones, one can separate the color into coordinates from blue and red. You see, in our case, for increasing the pressure, we succeeded to separate the colors blue and red contribution. So given that, one application could be as follows. So I grew in Istanbul, and at those, when I was young as a kid, there was only one bridge connecting between Europe and Asia. So before entering the bridge, I remember the old trucks, especially field trucks, staying on the right-hand side of the road, and they are waiting for something. So now I understand the engineers want to understand the weight of the staying on the bridge, okay? So because if you cannot control the entire stress on the bridge, so it may deteriorate, it may increase the mechanical failure. So this is because they want to know the entire mass on the bridge, and these trucks, particularly the field ones, are waiting for something, to know the mass of the trucks. Even that, you have a kind of litmus paper, so you can give them, and the truck pass on the surface of the material, and it turns into somehow red. Depending on the structural coloration and depending on this process, one can readily understand the total mass of the truck filled with product. So it can be one good practical application for such kind of material. So interestingly, when we apply mechanical pressure, we realize some crystalline domains in the structure of polymer. So in electron microscope image, you see some rice-like structure. They most probably are crystal induced by high pressure. So we follow the crystal formation in diffractogram blue one, the initial one. After application of mechanical force, you see new set of reflections, and it shows the formation of crystals. Polyacrylamide is a self-healing material. We cut into 2 pieces. We put in a humid environment. It swells. These 2 pieces of polymeric structure merge each other. They start to establish the hydrogen bonds again, and it returns back after say 1 week. Okay. So this colorimetric change occurs one after the other. After 3 cycles, we have almost same blue color and same red color after application of pressure, and it is a self-healing material. I think my time is running out. Then I want to make an overall conclusion. So in the last 45 minutes, okay, I showed you 3 different mechanical sensor systems. 3 different pigment systems, say. One was triboluminescent material. We mentioned about red and blue type of triboluminescent material with different organometallic chemistry, and they can be used as an impact sensor material. The second one, structural coloration using polymer and silica colloids. We succeeded to obtain different colors, then they can be used as stress sensor material. And for the last part of the talk, I showed you the assembly and disassembly of gold nanoparticles, and they have the entirely different colors, and they can be used as a pressure sensor in polymeric systems. And I want to thank my group. In fact, using this topic, I finished 2 TÜBİTAK projects. I have to thank TÜBİTAK for the financial support. And these 2, one gentleman and one lady staying on my left-hand side, the guy is Gökhan Topçu, and he did PhD with me. Then he went to Koç University postdoc, then Warwick second postdoc. Then now currently he is a chief engineer in Liverpool in R&D department of Unilever. And this lady, Ezgi did master study with me. Then he moved to Germany for PhD. Several months ago, she finished her PhD. Now she's working for Bosch company as a process engineer. Okay. So, by the way, this TÜBİTAK projects finished 5 years ago, and your invitation was a good opportunity for me to return back, and I want to be active, reactivate my research in this mechanical sensor field. Then two last pieces of photographic images. I know this is an event of Sabancı University, and I'm the first graduate of the engineering faculty of Sabancı University. So I'm staying on the right-hand side, okay, many years ago. So my advisor, Yusuf Menceloğlu, was staying in the middle. So last week I received a phone call from Professor Menceloğlu saying that he is not able to join to my webinar because of some health problems. I hope he will get soon well. And you see, I haven't seen him for a long time, but I always remember him as a active, young, and handsome professor, as you see in this photographic image. On the right-hand side, I was the first graduate, as I said. When I got acceptance from Max Planck Institute after my PhD, my classmates organized a farewell party for me. So, and this is a gift, this evil eye is a gift of Osman Burak Okan. He was undergraduate study at those days. The father was working for Şişecam, and he casted a special type of evil eye for me. This is the largest evil eye I have ever seen, by the way. So I still keep this gift in my room. It's staying on my backside. Okay. Then I have to thank Sabancı University Sunum for invitation. I have to thank Didem Taşçıoğlu and Nokta Hanım for their invitation and help. And thank you for your participation and your time.
Mustafa Hocam, it is our pleasure. Thank you. Dear participants, you can free to ask a couple of questions to Mustafa Hocam.
I think we have still time for questions.
Yes. Also, you can use chat box.
So I'm trying to. Can I stop share?
Yes, sure.
Okay. If you don't have a question, there are two options.
Hocam,
Either.
sorry, I can. Sorry,
Please.
sorry to interrupt you. Just on the like slide 15 to 19 about the triboluminescence. So I see the your like triboluminescence peaks. They are like either like signal to noise ratio is very high or like those peaks are very narrow. So like normally like the luminescence spectrum is very broad and uniform on slide 15 or 19.
Yeah, just let me see. Nokta Hanım sharing'i kapatabilir misiniz?
Tabii hocam.
Let me share again. Are you able to see the slide? No?
No.
Slide 15 is it.
Yes.
In slide 15,
Yes, about triboluminescence.
let me open from here.
Yes.
Maybe you are talking this one?
Yeah, this middle one, yes.
In the
So,
middle.
yes.
Yeah. But maybe I have to show this one. Yes. These are two representative ones. The blue one, yes, it is quite broad, as you pointed out.
Yes.
And red one is quite sharp. And it is nature of this European type of organometallic compound. So it's strange. It's look like almost a laser. Huh?
Yes.
So, yeah, this is nature of European tetrakis ammonium. It was quite interesting for me at the beginning. You're right. I was expecting the one on the right-hand side.
Yes.
But European tetrakis has such kind of nature. Yeah.
So this means like they have very intense emission, like this red one.
Sure. This is because we begin with this one. Otherwise, if you want to associate with polymers somehow attenuate the optical signals. You see many different types of absorption and scattering stuff when it impinges on a polymeric system. This is because we begin with europium tetrakis triethylammonium, and in literature, the synthesis is quite easy, and it has very high intense triboluminescent emission. We were lucky. We understood how can we make a composite material with triboluminescent material with this one. If
Mhm.
we would begin with the blue one, most probably we would give up because the
Mhm.
signal is quite weak.
Yes. Okay. So, like, just very maybe simple question, like, if like this has very intense peak, this
Mhm.
red one. So,
Mhm.
if we mix with some organic dye that absorb this light, it could be like it could be possible to make a composite system that makes an input for lasing, like organic dye will emit some light. Would it be possible? Because this is very intense. If power
Yeah,
is enough.
yeah, it can be, but I'm not sure whether power is enough for this application. But
Or
if somebody will begin with one of these triboluminescent material, it
Mhm.
should be this one.
Mhm. Okay,
Mhm.
like we can get like composite thing like triboluminescence and photoluminescence if we make
Mhm.
something composite.
Yeah, yeah.
Like, could it be possible through this one?
I think so. I think so. So
Okay.
in this slide, as you pointed out, left-hand side is photoluminescence in solution in water. So this is because it's quite smooth function. But
Yes, this is
in
clear.
yeah, in triboluminescent, you have seen different band gaps, so
Uh-huh.
it's not that much smooth.
Okay, okay. Thank you. Thank
Mhm.
you for nice talk with you.
Thank you very much. You're welcome.
Hocam, you can see some messages on the chat
Yeah, I'm
box.
trying to check.
They
Okay.
they thank you.
Hı. Evet Hakan Bey, özel görüşmeniz mümkün. Eğer mail atarsanız muhakkak webten bulabilirsiniz beni, Mustafa Muammer Demir. Tüm teşekkür eden arkadaşlarıma ben de çok teşekkür ederim vakit ayırdığınız için.
E, Başka soru yoksa hocamızı teşekkür edebiliriz. Yoğun programında bize vakit ayırdı.
Çok teşekkür ederim katılımınız için. Hakikaten çok memnun oldum. Dediğim gibi uzun zamandır ara verdiğim bir konuydu. Şu saatten sonra ben de tekrar geri dönmeyi düşünüyorum. Bu da vesile oldu.
Harika.
Bunun için çok teşekkür ederim.
Ne mutlu bize. Çok teşekkür ediyorum hocam.
Ben teşekkür ederim. Çok selamlar
Gerçekten
Sabancı
bugün
Üniversitesi'ndeki
evet,
arkadaşlarım.
sizin için de ekstra yoğun bir gündü. Çok çok teşekkür ediyorum. Katılımcılarımıza da teşekkür ediyorum. Önümüzdeki hafta sunum yeni araştırmacılarından biraz önce de size soru yönelten Muhammed Umar konuğumuz olacak. E, Değerli katılımcıları, bundan böyle her hafta çarşamba günü tekrar Nano Open'a bekliyoruz.
Çok teşekkür ederim. İyi günler dilerim.
Çok teşekkür ederiz. Hoşça kalın.